We wait just a minute to let people join in the session. Okay, so let's start. Good morning or good afternoon, everyone. Thanks for joining this session on ocean predictions from global to coastal scale. So today we are going to talk about best practices in this field, and just I would like to give you a brief introduction on this topic. So, as we know that ocean forecasting has become an operational service really recently, so actually since the early 2000s. And this happened also thanks to the advent of satellite altimetry, ARGO, floats measurements, for example. And it is also recognized that the definition of local bathymetry and coastline characteristics have helped a lot and have influenced the advances in ocean circulation at regional and coastal areas. So since then, significant progress has also been made thanks to optimizations, technological innovations, and those have somehow revolutionized the field of ocean forecasting from the global to the coastal scale. This has given rise to the definition of several best practices, as we know, and these can enhance and have enhanced our forecast accuracy and reliability that concerns many different topics, such as the choice of, for example, downscaling strategies, the choice of lateral boundary conditions, especially, of course, for regional and local forecasting systems, atmospheric forcing on one side and river inflows from the land, assimilation with mesoscale resolving models that consider complex geometries as well, but also best practices in validation of the analysis and forecast, as well as providing specific solutions for long-term analysis. Best practices has also helped us to advance in the definition of uncertainty thanks to ensemble forecasting systems that are becoming more widely used, and also for operational oceanographic product for scientific benefit. So today, with this session, we will try to tackle maybe not all these topics, but most of them, thanks to the participation of our 10 invited speakers that will provide their vision, feedback, and contributions to best practices related to ocean predictions from global to the coastal scale. So we have organized 2 sessions. One is going to start right now with 5 presentations. The other one is going to start in the afternoon, actually at 15 UTC, with the other 5 presentations. I ask you, the audience, to pose your questions in the Q&A bottom. You can see the Q&A bottom. You can already start including your question there during the presentation. We will have some time to raise your question just after the presentation of the speaker, or at the end of the session. We will have 10 minutes for open discussion. You can also raise your hand and we will give you the possibility to talk. So the agenda will start with Dr. Enrique Álvarez Fanjul. Actually, he's going to leave just after the presentation. So if you have questions for him, please try to pose your questions just after his presentation. Enrique is the Technical Coordinator of Ocean Prediction Decade Collaborative Center at Mercator Ocean International in France. He has a long experience in operational oceanography. He has developed operational ocean forecasting services and managed ocean measurement networks during his career. So, Enrique, it's my pleasure to give you the floor to start this session.
Thank you, Manuela. Thank you for your kind presentation. So I will share my screen and go directly to share my presentation. Oops, sorry. So to start this session, I think it's convenient to ask ourselves, okay, from global to coastal, how well are we doing this job in terms of ocean forecasting? And we had exactly the same question some time, 1 year ago. And what we did is asking the experts and asking the users, how well are we doing in this ocean forecasting work from coastal to global? And we asked several questions about the systems, the quality, the accessibility, and the timeliness of the ocean forecasting systems. And we asked this for different variables, current, sea level, ice, waves, and for different scales. And the results are quite interesting. This slide is the one with the answers from the experts, from the developers of the systems. And you know that in general, they are somehow not very optimistic. They are not super high qualification on how well we are doing in these different categories on the systems. Systems, how many systems are on the quality of the solution, on the accessibility of the solution, and on the timeliness. But it's true that for some variables, the situation is not that bad. Let's take, for example, waves. But it's also true that experts consider that we are doing better in the global, then a little bit not that good on the regional, and then the worst is on the coastal. So it's interesting to note that as we move from global to coastal, the experts believe that we are not doing that well, which is quite interesting, as you will see. You can see that also on the lower graphics, because you have here the global, regional, and coastal scale. On the global, there are many positive replies on the upper end, but when you go to the coastal, the situation is not that good. And also depending on the variables, you can see, and it's well known that our biological models are more complex and are producing results that are not that satisfactory as the wave models, for example. So this gives a good panorama of where the experts believe that we are. Remember, as we move from global to coastal, we are not improving, but the other way around. And this is in sharp contrast with the use of the systems. Here we ask to the experts, where do you use the systems? And we have here the different systems, and we have here the different applications. And as you can see, the global models are used. They are obviously very, very important because the other ones cannot be developed without the global models. But the use of the global models is limited just to a few applications. Then you go to the regional scale, and this is much more increased. And then you go to the coastal scale, and we are using the coastal ocean forecasting systems almost for everything. So consider that on the coastal scale is where we need more the ocean forecasting systems, and is where the experts believe that we are not doing that well. This is quite interesting. On the other hand, we ask the users the same question. Where do we think we are? And it's very interesting because the users have a very different opinion. The users believe in general that we are doing quite well with all the variables and all the different things we are asking for, accuracy, reliability. And there might be several explanations for this discrepancy. First of all, the experts know where to look into the problems. And second, and maybe more important, is that for the users, sometimes to have an indication is sufficient to do the work. They are not looking for a precise, let me give you an example. If the wave height is over 5 meters, I cannot operate. So what I need is this threshold, and I don't mind if it's 6, 7, 8, or 9 meters. I don't need this precision. I just need this threshold. And this is quite common in the users. So I think these two facts explain very well the fact that the users have a much better impression on what we are. By the way, we have 160 replies from the users, so it's quite a representative statistics. It was very well replied, this thing. So we know that our users are happy, we know that we are not that happy, and we know that we have to improve certain variables, and especially we have to improve on the coastal scale. So what can we do to promote ocean forecasting? From the Ocean Prediction Decade Collaborative Center, we are trying to do this through this virtuous loop, working on improving the knowledge, working on teaching people how to develop systems, how to operate systems, and finally, how to integrate systems. And for all these steps, we are developing different assets that I will explain to you now. So first of all, for reading our shared knowledge, we have published 2 years ago the TÜV's Guide. The TÜV's Guide is a publication that compiles the very basic about ocean forecasting, and we have converted this TÜV's Guide into a wiki site so we can incorporate additional knowledge into this. Every 2 or 3 years, we will create a new version of the TÜV's Guide. That's the plan. Then on the next step, which is the development of ocean forecasting system, we have built, by the way, it was published yesterday on the webpage of Ocean Prediction DCC, the architecture guide, and this is a community product now delivered. It was delivered yesterday, and it's a practical guide on how to wire an ocean forecasting system. And it tells from the high-level diagrams like these ones, where you have the ocean forecasting in connection with the digital twins. Those are the high level showing all the value chain, to the very detailed steps you need to do to operate, to build properly an ocean forecasting system. It's really a definition of the tools and data standards that need to be developed during the decade in order to build this ocean forecasting system in a very standard way, in a very robust way. These diagrams compiles the experience of many people that have been working many years on this topic. This is where you can find, so I just prepared this slide 2 minutes ago with the architecture guide now available on the web page. So you can download it on our web page. Also, we are working now in this field on the development of data standards. This is a work we are going to do next year. And we want to understand and to explain to people what is the correct way to store information about ocean forecasting, which is far from trivial because there are many things that have to be considered and are usually not that easily considered. Next step is how to operate the systems, how to run the system. And for that, we have built something that we call the operational readiness level. The operational readiness level is in reality a collection of best practices having on top a test to check how well you are doing with these best practices. And these best practices are in 3 categories: production, system validation, and product dissemination. Depending on if you are following these best practices or not, you are having different scores. So we are stimulating the introduction of best practices into the production of ocean forecasting. This is going to be published soon in the form of a peer review paper. We hope it will be published during this month. We are just on the final stages of this. And this is the list of best practices, and depending on how well you are doing with this list, you are advancing in the ladder and you're having different qualification that is giving you a hint or on the areas that you have to improve on your ocean forecasting system. This is not about an examination. It's providing the tools to help people to understand how well they are doing with the best practices associated to the operations of ocean forecasting systems. Then we have the integration, and in the integration we have the digital twins, the cloud, all these initiatives that are coming out, some European, some are derived from the decade. And we are working with all our colleagues of the decade with programs like Foresee, DTOS, and Best Practices, Coast Predict, and James Ocean, together also with the different DCCs and DCOs of the decade, trying to advance into this concept of one ocean, one digital ecosystem. And this is all the work that you have seen before is also closely related to this. So in conclusions, we know now that we need to improve our services. This is what experts are saying, especially at the coastal scale. Ocean Prediction DCC is doing several things, but one of the things that we are doing is developing assets that could be used by everybody for this tag. We have the architecture, the URL, tools for communication, and many more to come. So we are working together with dedicated actions in this direction, and please have a look to what we have at our webpage and register into our community at unoceanprediction.org. So thank you very much, and I hope I was on time.
Thanks, Enrique. Thanks a lot for this overview on the Ocean Prediction DCC, on the activities that you have developed since the beginning, since the start of the Ocean Prediction. So since we have some time, I don't see questions in the chat. I can just ask you, how do you think ocean best practices? You mentioned several times there's a strong link with the ocean best practices. How your work will benefit from ocean best practices?
I think we have a very close connection with the program of Ocean Best Practices, with the Decade program, and this was put into practice in the creation of this concept of the operational readiness level, which is a collection of best practices. In fact, it's a well-structured collection of best practices. And the idea is to continue this collaboration in two different ways. First, promoting the use of this operational readiness level concept worldwide, that will for sure help people to operate in a better way their systems. And second, giving more detail to some of these best practices. Some of these best practices in this, let's say, initial publication are somehow defined in a very loose way or without entering into details. I'll give you one example. One is we have a best practice that is saying systems have to be protected against cyber attacks. Okay, that's cool, but how do you do that? So now that we have this framework, which is operational readiness level, there's still a lot of details to advance and to polish and to move forward to help people in doing their systems properly. So that's it.
Okay, thanks a lot, Enrique. Yeah, perfect. Thanks a lot. So if I see no other questions, so we can move to the next speaker. So we move to Dr. Ivan Federico. Ivan is a scientist in ocean modeling at Euro-Mediterranean Center on Climate Change in Italy. He's responsible of the Advanced Coastal Ocean Modeling and Application Research Unit, with an expertise on high-resolution modeling, especially in coastal areas, local areas, using unstructured grid models. So please, Ivan, the floor is yours.
Thank you, Emanuela. Thanks all the panelists and the people that are here. Thanks for the invitation. So the presentation here is about the coastal scale. We have seen right now the importance of coastal scale, especially regarding the applications of the coastal at the coastal scale, which are the one that are most requested as the most intense in terms of also stakeholder needs. So in this case, we will show how we can reach the coastal scale through downscaling approach, downscaling ocean modeling, looking at the forecasting, and looking at this very close to the nearshore application. And this will also try to create what are the first driver for coastal digital twins. Basically, the presentation is organized in three parts. The first section where I will show a bit at CMCC what is our downscaling methodologies to reach the coastal scale via unstructured grid models. And I will show an application very close to the urban oceanography, the one related to the operational storm surge forecasting and the capacity of production what-if scenario for the area of Venice Lagoon with the usage of regulated barriers. And then I will show our chain of multi-model, multi-physics, multi-model that try to list multi-hazard to build coastal digital twins. And then, of course, conclusion and next step. Let's start with our downscaling capacities. CMCC invested a lot on the model at the coastal scale, limited area model at the coastal scale, with downscaling starting from the Copernicus. In the last year, we built several systems, most of them forecasting systems, some of them relocatable system operating for forecasting also. You can see that we cover a large region of the Mediterranean Sea, but also other European seas and extra European seas, where we have some partnership with different institutions. Of course, our goal is to reach the coastal scale, both for circulation and also for the waves in this case. And we have seen that the waves at the coastal scale, also by the presentation of Enrico, are the one that we have a measurement, we can also validate, and we can move to have also coupling between the wave and circulation. I'll show here just some example of these downscaling capacities with different focus related to the application. For instance, we have one related to the continuous between ocean, sea, and rivers. And so the possibility to also look at the phenomena which are closely related to the river sea continuum, such as the sediment transport dynamics. Other application that we have done in Ionian Sea related mainly to support the forecasting of the oil spill and reaching the highest resolution in the harbor areas. Cross-scale application for sub-regional and coastal modeling, starting from the Adriatic to the coastal scale of the entire coastal area of the Italy and the other regions in Adriatic Sea. Other application that we have developed with respect to the storm surge forecasting. This one is in the area of the Georgia coast in South Atlantic Bight, and is oriented to provide storm surge forecasting during extreme events. And also connectors application that has the function to connect the CMEMS regional models, the one for Mediterranean and Black Sea. And so to highlight the importance of the strait dynamics as input for both basins, the Mediterranean and the Black Sea. And the other that are very close to the urban ocean and the human intervention. This one is, for instance, this application that we have done for the area of Dubai, and where we reach this very high resolution coastal urban scale. Okay, here I reported just what I just explained, the river sea continuous, port and oil spill application, cross-scale forecasting, storm surge and compounding effect, strait dynamics, and the urban oceanography. This is an introduction to have our showcase of the different application. Now I will show one related to the area of Venice that want to enforce in terms of best practice. What are the link between the parent model, the regional scale model, such as the Mediterranean forecasting system in this case, and our very limited area model with hyper resolution in the urban area of Venice. In this case, we have built a setup of the model that should have should produce forecasting in case of storm surge events such as the Acqua Alta in Venice, and that what we have the opportunity opportunity to develop here is the introduction of these regulated barriers that are active in Venice during, could be acted in Venice during the extreme events. And we have introduced this type of barrier in our limited area model via an usage of immersed boundary condition approach. Here I will not go into detail of this technical numerical implementation, but idea we have the possibility to enforce some elements which represent the barrier as a solid boundary condition that at runtime can separate the two environments, the outside the lagoon and inside the lagoon. The benefit of the parent model, we can see that outside the lagoon we are forced by the Mediterranean forecasting system, which in this event, which is a realistic event that we had in November 2022, we have a forecast 3 days in advance. Here reported the observation and the forecast with different time leading, and we can see that with 3 days in advance, the Mediterranean forecasting system outside the lagoon have a good accuracy with just an underestimation of 2 centimeters of the peak. So we start from this boundary condition, and we can look at the result inside the lagoon, the propagation of the information by the parent model in our limited area and urban scale model. We separate here the tide gauge between outside tide gauge and inside the lagoon tide gauge. And of course, since we have introduced this module of barrier activation via immersed boundary condition, we can see that we can have in the period that the barrier are activated, this is the realistic case, we have this gray area which represent the activation of the barriers. First, looking at outside the lagoon, thanks to the benefit of the parent model, we can see that we propagate and we have a good agreement with the observed tide gauge. But what is important to see is the benefit of using our strategy of modeling with the inclusion of the barrier. And we had the possibility to compare with the different tide gauge inside the lagoon. And we are very close to the observation, and we have also the possibility to do some simulation in what-if scenario mode, for instance, without the usage of barrier. We have this damping of the wave, in this case that range from 90 centimeters to 1 meter. So this is an application of benefit of the unstructured grid model downscaled from a consolidated operational forecasting system that is able also to have the storm surge forecasting, the benefit for the coastal community when we are trying to simulate this case with barrier activation, and also the possibility to produce what-if scenario to use different timing of activation of the barrier. So it I think could be a good tool to produce what-if scenario for communities and for the operators. Going to the last part of the session, this type of approach has been integrated with different physics in order to have what we call a coastal digital twin. It was mentioned also in the presentation of Enrique. We have a lot of definition of digital twin. The one that I prefer is a digital representation of physical reality using model and observation, model and data. Digital twin allow to integrate multiple physics, allow to produce short-term forecasting, allow to introduce a fusion of modeling and observation, element of artificial intelligence, should have a characteristic to have end user usability and the capacity of production of what if scenario, as we have seen also in the case of Venice. And what is a key ingredient is also the capacity of relocability. Our integrated and realism augmented modeling chain take into account waves, circulation, vegetation inside the ocean, such as seagrass meadow, and also the interaction with sediment, in order also to produce this chain to provide information for downstream application for impact models, such as the one related to flooding. Here I show just some showcase related to some different hazards, the one related to the storm surge. This is the case of Mediterranean tropical-like cyclone, where we have the possibility to integrate wave and circulation to account the contribution of the wave to the storm surge, and how we can improve the forecasting. Then we have other type of assessment related to the nature-based solution. We had the possibility, thanks to the data fusion, to include in our modeling chain the seagrass present in this area, which are in the Tyrrhenian Sea in Western Med, and we can quantify what is the impact in terms of wave damping over this media related to the extreme events. We can also quantify in terms of site of interest community which are present in the area, and also this could be a study that could provide information also for restoration and reimplantation activity. I mentioned the part related to the flooding. Flooding as a downstream model could give us the capacity also to produce what-if scenario, which is one of the key elements that we have seen in a digital twin. For instance, here we have this application developed with the University of Bologna of downstream model in the area of the Emilia-Romagna, with to look at the flooding extent when I use the dunes, natural dunes in this case, or without the dunes. So it's in this case also the capacity of production, different scenarios. And also here we have included in this chain of models also the interaction with the marshland. And it is important to see the effective role of the marshland in terms also to mitigate the peak of the event. Here we report this configuration, which is in the Georgia coast in South Atlantic Bight, where we have performance simulation, only ocean and river representation, and including ocean, river, and marshes representation. And we report here different point of control. And you can see that in case of ocean and river, you have just a shift of your in time of your time series of sea level, but the peak remains practically the same going upstream in the urban area, which is this point P3. While when you use the ocean, river, and marshes representation, you can see this natural effect of the absorbing the sea level by the flow by the marshes that reduce, damp significantly the peak in the very urban area, which is the community lives, and so protect by effect of the extreme surge event. And so this is a good point related to the preservation of the marshes.
Even 1 minute left.
Last line, sorry, maybe.
Okay.
Apologize for that. The other slide is the one related to the coastal erosion, the possibility to produce what-if scenarios of coastal erosion, for instance, for the construction of harbor jetties to look what are the area of deposition and the erosion that are generated with the building of human intervention. I just conclude summarizing what I said, and of course, one key element of a coastal digital twin is the production of, as we have seen, of what if scenario, but also the capacity of relocability, and we are working as next steps to include this capacity of relocability of these coastal digital twins. Thanks, that's all, and again, apologize for the delay.
Thanks, Ivan. Thanks a lot for this wide overview of all these applications, downscaling, processing, and unfortunately, we don't have time for questions. Maybe if there are, please put your questions in the Q&A chat, and then we will answer at the end of the session.
Okay,
so now we move to our next speaker, Dr. Marina Tolani. She is a specialist in ocean modeling and forecasting systems at Mercator Ocean International in France. She's the coordinator of the monitoring and forecasting centers of the Copernicus Marine Service, and she is an expert of digital model for EDITO. So I'm pleased to give the floor to Marina.
Thank you very much, Emanuela. And so I just share my slide. Put it right. Yes. Presentation. Okay, I hope you can all see the slide.
Yes,
so
perfect.
Good morning, good afternoon, good evening, depends where you are. So in my presentation, I will address the topic of the synergies between the Copernicus Marine Forecasting Service and Digital Twin Ocean. This presentation is done with the contribution of so many people that I can list all of them, but are all the people that are contributing to the development of the European Digital Twin Ocean platform, and all the Copernicus Marine partners that are internal at Mercator, and all the external producers. So it's a quite wide community that is involved. So I will just provide a very short recap for who is not familiar with Copernicus service on the modeling products that are offered by Copernicus. Keep in mind that Copernicus is not just delivering modeling products, but for this presentation, I'm focusing on this component of the service. And Copernicus is delivering ocean information from a numerical model with data simulation scheme for the global ocean, the Arctic Ocean, and on the European regional seas, with different production system that are displayed in this map, and thanks to the contribution of several partners. And so these models have a different resolution. So all these components can have different resolution, horizontally and vertical, and are delivering information model based in the past with the product that is called reanalysis, that goes back for several decades, so usually at least 30, 40 years, and are up to 1 year or a few months to the present, close to the present. And then there is the other core products, that is the forecast product, that covers the next 10 days. So we have generally a forecast lead time of 10 days, and we also provide 2 years back in the past, produced by this forecast, that are what we call analysis, or can also be called reforecast, or depends, whatever is the vocabulary you are more familiar with. And with these systems, so we are able to provide forecasts that are deterministic. Usually we run the forecast once a day, but it could be also twice. And mainly this is happening for the wave component. And for the multi-year, as I said, so we are usually starting from 1992 for all the products, and some are starting well before. A new time series for the multi-year is released every 3-5 years approximately, and they are regularly extended. The information are based on physical, wave, biochemical, and ice models for providing different information for the blue ocean, so all the physical variables like temperature, salinity, currents, sea level, mixed layer depth, and waves. Green ocean, for delivering variables as plankton, organic carbon, nutrients, oxygen, carbon, and system optics. And white ocean for providing different characteristics of the sea ice, like concentration, extent, thickness, type, velocity, snow thickness, albedo, and sea ice age. And with the development of digital twin ocean, we can further exploit and develop the Copernicus system from the two ways. So Copernicus can benefit of DTO, and DTO can benefit of Copernicus. So here there is a sketch of what is the digital twin ocean. I know that even in the presentation before me has already talked a lot about the digital twin ocean, and I think that most of you are familiar with the concept, but just to summarize, so the digital twin ocean is a replica of the real ocean that is built using satellite data, marine observation models, tools based on artificial intelligence, information coming from citizens of science that covers the different aspects of the marine environment. And the digital twin allows to make a knowledgeable decision for the ocean, because we can combine all this information together, and thanks to tools, it is possible to make a what-if scenario and to develop applications so that we can answer specific questions that can be raised and can be important for different communities. So it could be marine and coastal policies, researchers, blue economy stakeholders, every citizen, policymakers, and everyone really that has an interaction with the marine environment. And in Europe, since 2 years, has been started a project for developing a platform for allowing the development of digital twin of the ocean. And this platform is focused on a data lake that is giving access, a unique point of access to 2 European major marine assets, that is Copernicus Marine Service and IMODNET for in situ observation. But not only, there is can give access also to many other sources of information, marine information coming from different initiatives and projects. A component with an engine where there is a development of different tools and specific models, and that can allow to generate information that covers the physical, the biochemical, the ecosystem, and also the socio-ecological aspects that are linked to the marine environment. And so this platform is able to connect the European assets, science, and technology for being able to provide information on the marine environment. And so EDITO, that is the name of the platform that stands for European Digital Twin Ocean, is an evolution of the marine data portals, because it allows to explore, create, and contribute. So you can explore what is made available from the platform in terms of information, so in terms of data observation, but also in terms of tools that you can use. You can create, because you can also reference your own data, or you can reference your own tools, or you can develop there also your own tools and models for building the knowledge that you need to. And you can also contribute. It means that what you have developed and what you have contributed to can be made available to everyone, so that can be reused and exploited by other community. And so it should facilitate the scientists to do their work and reduce their costs, because we limit the data transfer from and will ease also access to the supercomputers. So will facilitate also the way you can contribute, improving the fairness and reproducibility of the information generated, and so is offering an efficient tools for an open and collaborative way that I think is really key. And here you can see in a different shape the same concept of this explore, create, and contribute opportunity that you have with the digital twin, that really is for strengthening the concept of this environment where you can collaborate, co-design, and exploit what others have developed in order to have a better information on the problem you need to address. And here this is the platform, how it is. So you can see on the top right the URL of the platform. And so it has three main components: a part where there is tutorials, where you can learn about what is available, and then there is how you can use the platform. It's always an ongoing project, and so things are continuously evolving. It's not static, and what you see there today could be improved tomorrow and in the months to come. Then there is the Data Lab. That is the place where you can design and run digital twin ocean applications using the tools that you are used to use. So there is a choice of options. And then you can explore oceanographic data. And as I said, we started giving a unique access to the entire Copernicus Marine and EMODnet catalog. And so you can explore the data, benefiting also of the viewing capacity that are there and will be further developed very soon. Here, without going into the detail of this structure, but just to prove that Edito platform is based on a set of standards and APIs that allow for an easy user interface. And so this should facilitate the interaction with all the community. So here again, just to remind you where you can go and find the information. And so in terms of Copernicus, how can Copernicus service benefit of the existence of the UDTO? So it can. So Copernicus is delivering all the products using the Marine Data Store, that is a cloud-based solution for providing all the service that Copernicus is provided. That is developed in collaboration also with the European DTO, that will allow to offer more, because European DTO can also offer tools that can directly in the cloud use the Copernicus information, making them more fit for purpose for a wider community of users, and also more flexible. And at the same time, Copernicus contributes to the UDTO because it's providing an important source of information. But what is really important for the
1 minute, Marina.
Yeah. Thank you. What is really important for the interaction is that we are now facing a new contractual phase in Copernicus, where we will aim with our producers to further benefit of the UDTO in terms of products and increase the flexibility that the user can have for downloading the products and accessing the products. And this means that there will be much more flexibility that will allow, especially for the coastal system, to access data that are not only from Copernicus, but also from EMONET in the same way, in the same place, in an harmonized way. And so this will increase they will increase the capability to use all the information that are available and that are needed for your coastal system, but also to have a more flexible access to information and to different grids and improved subsetter capabilities, so that you just get the information that you need, when you need, where you need, on the grid you need. That is something that today is not available yet. And so this will allow us to be really more flexible and close to the needs of research. But I like to close my talk with this sentence from John Bell, that he says that this is why we got to the moon and back. It is because people were inspired and people felt part of it. And I think that this sentence is important because it contains the key for a success of the digital twin. So we need to have the entire community that goes from a global, regional, coastal, ocean that feels inspired, and so that you can feel part of it, because without the contribution of the coastal component, we will never be successful in this effort of joint effort in the different component of the European marine assets. So thank you very much for your time.
Thanks to you, Marina. Thanks a lot for this nice and useful overview of Copernicus Marine Service and DTO and EDITO platform and all their connections. Unfortunately, we don't have time for questions, so we just need to move on to our next speaker, Dr. Anabela Oliveira. She works in the Department of Hydraulics and Environment of the National Laboratory of Civil Engineering, Lisbon, Portugal. She has an extensive experience in forecasting coastal dynamics. Her research combines computer science with coastal engineering to produce tools tailored to stakeholders' needs in multiple areas. And today she will present one of these. So please, Anabela, the floor is yours. We can see the screen, but we cannot hear you.
Can you hear me now?
Yeah.
Okay. Okay, so today I'm going to talk about how we can use computational services on demand to build reliable coastal forecasts. And this is a very important issue, because we need to make sure, as we spread our coastal forecasts throughout the world, that they can be audited, they can be replicated, and people can use it with trust. So just going back a little bit on the concept of forecast systems from our coastal point of view, there are several blocks that we need to attend. So we need to look for reliable, robust forcings. We need to have strong and robust prediction engines. And then we have a very important part, which is to be able to get the results of the forecast systems and make it available for users, providing them at the same time with the ability to compare with real-time data. Of course, the societal value for coastal forecast systems is well known. They are a fundamental part of the management of these systems, helping us to anticipate contamination events, support the water economy daily tasks for ports, for industry working on the coast. And also they can also help us to guide our management to minimize risk in the long term. One aspect of coastal forecast systems that people don't know is that as we collect the results of a forecast system every day, we build long-term databases. Finally, as some of the previous speakers already spoke about, forecast systems are a fundamental part of digital twins, and we need to make sure that they have the right quality for us to use them in this context. So this is, I'll go a little bit back to the way we handle forecast systems for a long time, and we have a very simple methodology. So we start by looking at what are the processes that we need to address in a specific site. There's no need to run very complex simulations if the processes are not important. Then after we selected the important processes, then we look for the spatial and temporal scales that our models need to address. And then we look for models that can solve those processes and on those scales. Of course, we then look at the validation with the historical data, and then we are ready to build our forecast systems. And while we do this, we need to make sure that forecast systems are robust, so they run every day and they don't have numerical problems, and that they provide good results. Then the next step is to integrate all of these into tools that the users can take advantage of. Of course, the historical way forecast systems have been evolving has been built on a case-by-case implementations, and this is a very large problem because forecast systems built this way are very difficult to replicate, and they are very difficult to update. So if we have a new version of the model, if we have a new data source, these independent islands, as I depicted here in the figure, become obsolete very quickly. At the same time, forecast systems require very large computer resources on the one hand, and they need the IT people to make it run and to make sure that they provide resources every day. So one thing that we learned very quickly is that we need to address this in a completely different way. So we're starting building our forecast systems as a workflow of different building blocks. And by doing this, we are able to improve our forecast systems in a very efficient way. So this sets the stage for the next step, which is we need tools to relocate our forecast systems very quickly. So rather than having one implementation, we need to have a tool, a computational tool, that allow us to model and predict a coastal system very quickly and in a way that it can be replicated and validated and assessed by the users. So here comes the concept of forecast systems as services. Doing an overview of what is available for these contents, for this goal, we identified a number of tools. For instance, we have already heard about SURF today, that can help us to build reliable, robust, and high-quality forecast systems. And out of these systems, we look into questions like the access is open, the source code is open, what do they provide? And here's a summary of that. Out of this, I'm going to talk about what we have been developing at LANEC for the last 6 years, which is a service OpenCoast. And OpenCoast, what is different from the other ones, it is very simple to use. It was conceived to be a forecast tool for the users, not for the scientists, although the scientists also use it, but for the users, for the end users to be able to build the tools they need for their activities. So what is effective OpenCoast? So it's a forecast service that allows the user through a web interface to build a forecast system. The user can select the choice of the forcings, the model parameters, and the data sources for the forcings, and also for the data comparison. It is able to integrate with the external forecasts, like if you have an AI model for your river flow, you can input it there as a web location. And it's very easy to replicate, for instance, to do a fast calibration of the model. OpenCoast also covers the whole forecast cycle. So you can create the computational grid. It's based on unstructured grids. You can configure your forecast, manage the list of your forecasts, and it has a quite simple viewer. Also, it has a very flexible IT architecture, so it can grow to additional processes, to additional models, to additional challenges. And it also takes advantage of the cloud resources of the ASK services. Just very quickly to show you one of the steps that the user follows to build the forecast systems. You can see in the top the several steps the user needs to accomplish to get the forecast system. And it is as simple as this. This is an example on how we integrate the data. So the system automatically identifies the nodes from the ModNet that are inside your computational domain and offer it to the user if he or she wants to use it, and also allows the user to create virtual sensors, so points where he or she gets the full resolution of the model as a time series. As doing a forecast system is not just creating it, we need to manage to see if it runs well. We have a manager that you see on the left, and we also have a very simple viewer that displays both maps and time series. Of course, OpenCoast is very nice and it is very easy to use, but our end users, we are a national research lab, need to have simpler things, tailored portals to their specific uses. So we built what is called coastal observatories that explore OpenCoast as a computational service and build what is needed for a specific project. And I have here, the next slides, an example from the Connect project. The Connect project is an observatory that is co-designed with the end users. So the end users were with us building the system from the start, having an intervention at requirements phase, and then having the opportunity to evaluate and to make suggestions. So for our forecast systems inside Connect, we have two systems, the Tagus estuary and the Mondego estuary. And here I'm going to show an example for the Mondego estuary. This is a narrow estuary with a long river input. And our questions here were navigation, estuary inundation, and water mass characterization. We have important end users here, a port, an important environmental reserve. So we had to balance the different uses and the interventions in the system. So we developed a 3D forecast using OpenCoast, the service. And this forecast simulates water levels, velocities, waves, salinity, and temperature. And in order to build it, we went to our portfolio of 4 things and selected the ones that provided the best results inside the coast and the estuary. And you can see that by doing a downscaling based on the local, regional, and global products, we are able to go to very fine resolutions inside the estuary. So this is an example of what the user gets when he enters the portal for this specific site. So he gets both the results of the model on the left and an overview of the recent data on the right. And this screen is configurable. So if the user wants to put a different variable for the model results or a different data source, he can on demand create those services. Also, as forecast systems require a lot of validation from the user, so they can take decisions in a meaningful way, we created a number of products that can help them to have the information tailored to their needs. So we have the full information from the 3D forecast, the capacity to build virtual sensors, and then all the parts related with building trustworthiness in this forecast. It has to do with data model comparison using both Copernicus remote sensing data and local sensors from the CoastNet infrastructure. Then we have a model performance and the quality assessment for the past few days, and the capacity to look at weekly reports that evaluate the quality of the predictions. Finally, as one of the goals here was also to address some European directives, we also built a specific dashboard for the indicators. So basically, what are the conclusions from what we have learned so far in the area of on-demand forecast systems? Most of the times, the complexity of the coastal dynamics, the myriad of tools that are available for the modeling, and the need for computational resources are a challenge for most users to set up good quality forecast systems. From our experience, the use of high-resolution models that are freely available and along with the near real-time data sources can support the building of good quality forecasts. But typically, the IT implementation brings additional challenges. So our view is to look at computational services like OpenCoast to help the users to build forecast systems that they know they comply with what quality standards to build a forecast system. They are sure by using OpenCoast and other tools that the connections with the CMEMS data is well done, that the identification and link to the ModNet stations is well done, and they have trust in what is being produced. So OpenCoast is just an example of a computational service that can help users in that regard. And there are other helpful tools that can help users to build reliable and robust forecast systems. And I think it's a very important issue as we want these type of systems to be implemented throughout the world. An issue that I didn't talk about that is also part of our ongoing work is the link with the artificial intelligence. And it can play at the coast a very important role, in particular to handle the land inputs, both from the river, as part of our rivers as dams, so we cannot just run river dynamics models, and at the same time to handle the inputs from the cities, from our wastewater discharges, from our overflow discharges. So there are a lot of work to be done there, and AI has an important role. Also, we can use, like it's been done in Edito, AI to build fast predictors based on our process-based simulations. And that is also very important at the coast. Finally, an issue that it is very important here is the human in the loop. We need to make sure that our forecast systems are promoted by our users, accepted and used by our end users. And to do that, we need to have people at the requirements phase and to give them the opportunity to validate the quality and contribute to the improvements of the systems. And I'll just finish saying that the last slide you saw from the Connect project is being funded through the Downsync program of CMEMS, as shown here on the slide. Thank you so much for your attention and entertain any questions you may have. Thank you.
Thank you. Thank you very much, Novella. Very, very interesting presentation on these useful on-demand services. So no time for questions. We just now move to our last speaker, Dr. Mike Ersfeld. Mike has a long experience in studying regional areas in regional seas, including modeling of the ocean physics, the development of satellite processing systems, and also biochemical models. He is an hydrodynamic modeler at CSIRO in Australia. He works within the coastal environmental modeling team to maintain, develop, and apply hydrodynamic models. So please, Mike, the floor is yours. Okay, we don't hear you. I think you have the microphone switched off. We see the presentation in presentation mode.
Yes, I'm going to need that, aren't I? Yep. Okay, let's try again. Yeah. I'll just find my presentation. There it is. Okay, how's that looking?
Yep. Just put in presentation mode and that's fine.
Right, good. Are we good?
Yeah, perfect. Thank you. Yeah.
Okay, thanks for the introduction. Right, I'm going to talk about a case study of downscaling to the Australian-wide continental coastal scale. And the Australian government has a plan, a national marine science plan. And within that plan, there's a number of recommendations. And one of them is to develop a national marine information system. And I've been tasked with a few other people to forward that. Currently, there is no such national system in existence. We've got global models that have mesoscale capability, and they're quite good. And there's a patchwork of regional models, which I've shown in some of the pictures at the bottom. But there's no coordinated connectivity between these models, and they're all quite disparate. So there's no coordinated true national coverage at the coastal scale. And by the coastal scale, I'm talking about scales capable of resolving sub-mesoscale dynamics, and we're sort of looking at target resolutions of 1 kilometre to do that. So what we're aiming to do is develop an Australian national model capable of resolving coastal dynamics, because that's the gap in the system at the moment. So if you were to do that, the brute force approach would be to put a big rectangle over the country, but the country is pretty big. It's 5,000 by 4,000 kilometres. So if you're going to resolve that at 1 kilometre resolution, you're going to end up with over 20 million surface cells, and about 40% of those are wet. Dry, sorry, 60% are wet. And there's lots of areas in this domain in the corners in the deep ocean that aren't coastal, and you're not really interested in simulating them. So it's not a very efficient way of doing things. An alternative will be to make a cyclic grid, cyclic structured grid that's coastally fitted, and you wrap it around and make a cyclic join at some point in your domain. And that ensures that everything's within the region of interest. And with around 2 to 5 kilometre resolution, you end up with 1 million cells, which is still a lot, but it's in the right direction. However, only about 18% of those are wet. So you've got about 180,000 wet cells, which is heading where you want to go. But these cyclic polar grids are very difficult to build. And the reason for that is that the cyclic join has to match up exactly, so you can make the cyclic condition, and that's not easy to achieve. So it's not really a flexible option either. Another option is to use unstructured models, and these make a mesh within a convex hull, so you don't need a join. And resolution can be placed exactly where you want it, and resolution transition can be managed pretty easily with a weighting function. And this is an example of such a grid where we've used a weighting function that's the distance from the coast. So the further away you get from the coast, the coarser the resolution gets. And with 1 kilometre coastal resolution, we end up with 1.25 million surface cells, and they're all wet. So this is suddenly starting to look like a manageable situation. It's a big model, but global models are bigger, so it's doable. So we decided to have a crack at it using this approach. And we're using an unstructured model that we've developed in-house that's based on the MPAS-O global ocean model. So it's basically a coastal version of MPAS. And this uses a dynamic core called TRISC, which was developed by Todd Ringler, which is a C-grid polygonal mesh on a Voronoi diagram, which is basically hexagons for a uniform grid. The model has some nice properties. It conserves volume and mass, which is good, but it also conserves vorticity. It supports a stationary geostrophic mode, which not all unstructured models do. And most importantly, it requires no stabilization. And if you look in the fine print for a lot of unstructured models, they'll start talking about stabilization, which is basically filtering of unwanted numerical modes. The meshing is also quite well handled. There's a mesh generation package called Jigsaw that was developed by Darren Nguerda, and that was developed specifically to conform to the numerical requirements of TRISC. So it's designed to accommodate all of the things that TRISC requires to remain stable, and it does result in very high quality meshes. So we've built this model, and we've downscaled some of the operational products that are available in Australia to drive it. Where these products were developed by the Australian Bureau of Meteorology. They have a global ocean model called Ocean Maps, which is based on the MOM6 code. It's 10-kilometre resolution around Australia, and it supplies all of our initial and boundary conditions. They also have an atmospheric model that's based on the unified model from the UK Met Office. They call that Access, and that gives us 12-kilometre resolution around the country and supplies all of our surface fluxes. So we've gone ahead and built a model based on this coastal MPAS model using these forcing products. And one of the themes, or a few of the themes that I noticed for this session were open boundary conditions and riverine conditions. So I just want to spend a little bit more time talking about the detail, the technical detail of the conditions that we use in this model to build our open boundary conditions and freshwater influxes. And things are a bit more complicated for unstructured models than structured ones for open boundaries, because firstly, there can be more than one edge, normal boundary edge that's associated with a cell center. These blue arrows here on the diagram on the right, which means more housekeeping. In structured models, you always have one normal edge. And also you're not guaranteed to have a cell center that is perpendicular to the open boundary cell. A lot of these radiation conditions you use for open boundary conditions assume that transients approach the boundaries at right angles, and that's not always easy to accommodate in these models. So we've taken a different approach that's based on something we've developed for structured models, and we use a clamped or Dirichlet condition for all of the velocity fields in the boundary cell. And I know that Dirichlet conditions are a bit of a no-no, but it does depend how you implement them. And by implementation, I'm talking about the relative position of your normal boundary vector to your cell center. And most models will use an inner implementation where the normal boundary vector sits inside the cell center, as this white arrow would be here. And that's done for historical reasons also because it's easy to implement. If you have an outside implementation, the blue arrows here, then you do need to have additional edges in your model to accommodate that. So it's a bit more housekeeping. But if you do that, then you'd notice that your cell center is perfectly constrained with fluxes around it. So you can compute your cell center variables, elevation and traces, using mass and volume divergence the same as you would everywhere else in the interior of the domain. In other words, you don't need a boundary condition for elevation. And that's really important because it's usually as soon as you start messing around with elevation that you run into boundary specification issues. In this case, it's perfectly specified because it's responsive to all of the fluxes that are going in and out. But the problem with that is that normally your cross-sectional areas between your parent and child boundaries are not the same because you may have different bathymetries and interpolation error, and that can cause basin-wide divergence that causes your domain to fill and empty over time, which is no good. So to get around that, we have a local flux adjustment to compensate for that. We don't want to use an integral flux constraint, which exists because we do want our basin to fill and empty on short timescales, for example, when the tide comes in and out. So we need a local adjustment, which basically says what elevation do we want in that cell, which would be your parent elevation plus maybe the tide plus maybe inverse barometer effect. And then it inverts the continuity equation and figures out what fluxes are required on the boundary, what normal fluxes are required to achieve that target elevation. And then it'll relax towards those target fluxes on some timescale tau, where a short timescale would be more active condition and a longer one would be more passive. So the important thing to note about all of that is you're still not touching elevation. That's computed by continuity and responds perfectly to transients going out or incoming data that you're forcing with. This whole scheme is very well suited to unstructured models with arbitrary polygons. And this is what we've implemented in the model, and it turns out to be quite robust and accurate. You can extend that to freshwater inputs and simple inlets. And the problem with those simple inlets is that you never really know what depth the halocline is going to sit at. So you don't know over what depth to distribute your fresh water. And we can, using this boundary condition, we can approximate that. Firstly, using a very simple relationship that Cooligan built a long time ago. That will give you a depth of a halocline. And then we prescribe a parabolic velocity profile over that depth where the integral of that profile is equal to the flow that you want coming in. Now, the unique part is that we include a ghost cell next to the simple inlet as a center, which is in this little diagram down here. And this is where we prescribe temperature and salinity. So your salinity would be prescribed as 0 if it's fresh, and temperature, whatever you think your river temperature is. If you've got T&S, you can compute density. If you've got density, then you've got a density gradient between your first boundary cell on the interior and this ghost cell. So you can compute a baroclinic velocity contribution, which you can then add to your parabolic velocity profile. And this baroclinic contribution is supposed to emulate your salt wedge circulation. So you will get inflow at the bottom and outflow at the top. And once you've done that, you can modify your ghost cell with an upstream advection boundary condition. So if flow is coming out of the domain upstream, the ghost cell gets saltier. And if it's going into the domain at the surface, the ghost cell gets fresher. So this is a very easy way to get fresh water into your domain. The alternative, what you'd normally do would be to resolve your estuary up to beyond the tidal limit. And if you're looking at a country like Australia with thousands of freshwater inputs, that's a pretty time-consuming process. So having a simple inlet that doesn't have a numerical response, which many of them do, because of the fact that they're not dynamic and you don't know over what depth to prescribe the fresh water, having that capability vastly simplifies a downscaling if you're doing it at a continental scale for something the size of Australia. So just to finish up, we built this model and we ran it and we looked at some output compared to observations. This is just one example of some upwelling that occurred in 2017 off the southeast Australian coast. This is the model out of the box, so we haven't really tuned it at all, and the results are really quite encouraging so far. It's picking up the major features quite nicely. I think I might leave it at that. I'm going to play an animation of sort of the model as it stands to give an idea of the scale of the problem that we're dealing with, and maybe I'll just leave that running while I take questions. Any questions?
Thanks a lot, Mike. Thanks a lot for that. I don't see questions. First of all, thanks for sharing all these details on your structured grid model. Very, very nice and very interesting.
May I add a question?
Yeah, Ivan has a question. Please, Ivan.
Thanks, Mike. Very interesting, the approach. I have just a general question related to the Voronoi grid. What is the benefit of using Voronoi grid with respect to the triangular, standard triangular, let's say, grids?
Yeah.
Why is preferable to use Voronoi in this case of application?
Yeah, so it's well known that if you have sea grids are useful because they're good at resolving gravity waves, but it's quite well known that if you have a sea grid on a triangular mesh, it makes numerical modes that are hard to control. The Voronoi grid doesn't have that problem. If anything, it generates long wave modes, which are easily controllable. So the reason that we use the Voronoi mesh is because we want to use a sea grid because of its nice properties for resolving gravity waves, but you can't easily do that on triangular meshes without generating numerical modes in the form of checkerboards.
Okay, thank you. But you have also the dual grid that is triangular, so some approach of the dual grid of the triangular grid are also taken into account in this kind of project. Okay, thank you.
There are some models that I think Icon out of Hamburg uses a triangular mesh with a C grid, and they use some form of filtering to get rid of these numerical modes. So it can be done, but another way around it is to use the Verona mesh, and then you avoid the problem in the first place.
Okay.
Okay, thank you very much. So we can open the floor to open questions. Just a brief comment from your presentation. So it's clear that there is a strong interest to proper model coastal areas and to improve and to use new and more reliable strategies to go towards the coast, from the global to the regional and to the coast. So the importance of downscaling and information of high resolution bathymetry and information on the coastal processes are very relevant for that. We have also seen digital twin, how digital twin of the ocean is evolving, which are the applications, and how relevant is this framework in developing ocean forecasting, so for needs of our users. So maybe I can go with a general question for all of you, so please feel free to answer. I would like to ask you which are the major challenges that you encountered in your work in relation to the use of best practices, and if you can describe the potential solutions that could be taken to overcome these challenges. I leave the floor for any of you who would like. Please, Marina. Yeah.
So thank you. First of all, thank you to all the speakers, because it's been a very interesting session. So I've learned a lot of new things. So in terms of my challenges, so I have a long expertise in ocean forecasting, but now with the DTO, we are going beyond this, and we are trying to engage with different communities. And I think that this is the biggest challenge, because when you have to deal with different communities, you need to find a way to successfully engage and understand each other. And this needs to happen step by step with a lot of patience and respect. But I think that opportunities like, for example, this set of workshop is very important, because also for a session that we had yesterday, so we had to work together for preparing the session, and that was already a good way to share, even if maybe unconventional and not a standard process. But I think that dialogue, effort in understanding the reason behind choices that could be different from what we are used to, and so being very open-minded, can really help in embracing a wide community. That is what the Digital Twin Initiative is aiming to at the end, because you want to have information and tools that are encompassing all the aspects of the marine environment. And this means that you need to be ready for a huge variety that could be difficult as a first approach to fit into a standard and into a best practice. But I think the dialogue and the open-mindedness is the first step for fully and successfully engaging in this process.
Yeah, totally agree. This is a very important challenge, and the effort that you are undertaken is very useful to reach this objective. Other comments? Yeah, I see. I don't know who was first. I leave the floor to Annabella and then Ivan. We have like just a couple of minutes, sorry, then I think that everything will close automatically. So please, Annabella.
Okay. So the challenge that we faced here was to look for ways that the numerical modeling and the forecasting could be auditable by others, could be quality controlled, and to be make available to the users in a way that they can really use it. Okay, those were the challenge from our point of view. And I think that those are base questions that everyone needs to assess to a new forecast system. And basically the way that we looked for solutions for this was to try to look or to build tools that can be applied anywhere. So tools that can be relocatable and tools that can be built in an automatic way through the building blocks concept. So people know that if they use that tool and selected one specific building block, that it would be properly done.
Thank you. Yeah, yes, very, very important for sure. I'm sorry we don't have time for other comments. We just need to close. I would like to thanks a lot all of you for your very interesting presentations. And I would like to also thank all the participants. I remind you that we have a second session at 3 UTC. And so I guess that you will also join our next 5 presentations. Again, thanks a lot. Sorry, Ivan, for not having time for
No worries.
giving you the floor. Thanks a lot. Bye.
Bye. Thanks, Emmanuel.
Bye.